Okay, our next speaker is Emanuel Malek. He will tell us about recent advances in supergravity and puzzles for AdS CFT. Please.
Okay, thank you very much. So this talk is a little bit of a mirror of Alejandra's talk, very much coming from the supergravity side and trying to see, using some recent techniques we've developed, trying to see some new features in CFT, and also, as you will see, some strange things that we don't understand that I think fit very well into this workshop. So the AdS CFT correspondence really tells us that we can use string theory to perform computations to learn about strongly coupled CFTs, and a very nice target for what to compute are 2-point and 3-point functions of the CFT. In principle, if I have the 2-point and 3-point functions, I can get all the other correlation functions using OPEs. Having said that, despite several decades, 20-ish years of AdS CFT, computing the 2-point and 3-point functions has remained very, very difficult in the supergravity side, and in particular has only been possible when the backgrounds are very symmetric, in particular maximally supersymmetric AdS backgrounds. One of the reasons why this is so difficult is because, in particular, some of the 2-point functions are no longer protected by supersymmetry if you're not maximally supersymmetric. And so this makes it also very interesting. This really pushes you away from the many techniques that have been developed which focus on really supersymmetry, protected observables, supersymmetric indices, and so on. To get these kinds of computations in non-trivial examples with less supersymmetry, we really cannot rely on supersymmetry at all. So in particular, 5-ish years ago with Henning Samtleben, we sat at a workshop similar to this, a very nice workshop. And we thought, okay, well, what do we need to do to actually compute these objects? And this talk is very much about the road that this led us on and the kinds of techniques that we developed. And in particular, one of the nice things has been that we've really come across some very interesting features in CFTs, and there's been a bunch of puzzles. Okay, so what do we actually need to compute in the supergravity to obtain the 2-point and 3-point functions? Well, firstly, CFTs are very nice because we have so much symmetry, so the 2-point functions are completely determined up to a number, the conformal dimension. So how do I compute the conformal dimensions in supergravity? Well, it turns out that conformal dimensions are just related to the masses of my fields in supergravity. That's nice. But I have infinitely many fields in supergravity because I'm looking at some kind of AdS compactification, so some AdS times some compact space, typically some sort of sphere. So I get infinitely many fields organized in Kaluza-Klein towers. So the question then comes, how do we compute these Kaluza-Klein masses? You can ask the same questions about the 3-point functions. I'll come back to these at the end of the talk. The 3-point functions in the CFT are defined up to just a number, some kind of structure constants. And it turns out these structure constants you can basically read off from the cubic couplings in supergravity between all of these Kaluza-Klein fluctuations. So understanding these Kaluza-Klein fluctuations is important. Now, if you've only ever done this in your master's course, you think it's very simple. This is what you would normally do. You take a massless scalar field, for example, or Minkowski times a circle. Let S1, the y-coordinate be the coordinate on S1, x the coordinates on the Minkowski space. Well, this is the free scalar field equation. Because I'm working on S1, I can just do a Fourier series in the y-coordinate. And then everything is very simple. The Fourier modes are eigenmodes of the Laplacian on the circle, which is just the second derivative. And so I immediately find the usual mass relation in terms of the eigenmodes. Okay, this is very nice. Why is this more complicated in supergravity? Well, because the theory is much harder. So in supergravity, I have complicated equations of motions, mixing the metric and the fluxes. And for the masses, I only have to work with the linearized equations of motions, but still these are very complicated. Just to remind you how complicated these are, this is one of the equations of motions you get in 11D supergravity, where you have a background 4-form flux, a background metric that I haven't written explicitly, but is in the connections and raising and lowering indices. And then I also have 4-form fluctuations and metric fluctuations, little h. So this would be the linearized equation of motion And then you have to try and understand what are eigenmodes of this. This is extremely difficult. And as a result, this has only been possible for two very special cases until recently. The first case is where I only look at the Kaluza-Klein tower spin 2 fields, and the other case is where I look at very, very symmetric examples, so where the compactification is a coset. And in particular, this had an interesting application in AdS CFT in the early years, even working with T11, which is such a coset space where you can indeed use group theory to compute all of these. But for more general backgrounds, there's nothing, there used to be nothing you could do. But then Henning Sandleben and I, we came to this problem from a very different perspective. We came from the area of consistent truncations, which allow you to compute these masses for a subset of the Kaluza-Klein fluctuations. So what are these consistent truncations? Well, a consistent truncation is where I keep only a finite subset of fluctuations around some backgrounds, only finitely many fields. I get some lower dimensional theory, but I want to keep these fields in a full nonlinear fashion. Then I have some lower dimensional theory with some potential that I can study. Okay, so far so good. But now, because I'm keeping some modes and getting rid of other modes, I'm not guaranteed that solutions of this low dimensional theory have anything to do with my original theory. So a consistent truncation is a truncation where I keep the subset of fields in a clever way such that all of the solutions of my low dimensional theory are solutions of the original theory. If I do this, then I can compute the subset of masses that I've kept in the truncation for any of these solutions. As an example, this works for type 2b supergravity on around AdS 5 times S5. This would be, because it's just around S5, we can compute the full Kaluza-Klein tower. And it turns out there's a consistent truncation where I just keep these three sets of modes encircled here in red. These define some 42 scalar fields. This would be the potential of these 42 scalar fields. This is just some subslice. And there is a consistent truncation, meaning that any solution of this potential corresponds to some solution in 10-dimensional supergravity where the 5 sphere is deformed in some interesting way. And in particular, because I've kept some modes in the truncation, I can compute what happens to the 42 scalar fields that I've kept in the truncation as I deform the 5 sphere. But in principle, you would think I lose all the information about the other Kaluza-Klein modes that I've not kept in the truncation. But it turns out, as Henning, Sandleben, and I realized, these consistent truncations have very nice geometric properties, and these nice geometric properties allow us to actually recover all of the information about the higher KK modes that you get rid of in the consistent truncation, and so you can use these nice geometric structures that these backgrounds have to compute all of the KK towers and their masses and their interactions for a variety of examples. And to do this, you have to use something known as exceptional field theory that I want to just quickly tell you about. Okay. So how do you construct these consistent truncations? Well, we want to perform some truncation where I keep a subset of modes of some lower dimensional theory, and I want to embed these modes into the full 10 or 11D supergravity in some complicated way, such that all the solutions of the lower theory are solutions of the original theory. This is very difficult, and whenever things get difficult in physics, we rely on symmetry, and it's the same thing here. We'll have to use some symmetry arguments, and the symmetry arguments that we're going to use are left invariance arguments using group manifolds. So if I have a group manifold, then I have two very nice things that make this procedure straightforward. I have a global frame, my left invariant frame, and moreover, because of left invariance, this frame closes into an algebra under the Lie derivative. So if I take the Lie derivative of two left invariant vector fields, I get the structure constants of the Lie algebra of my group. And it's very easy to show that if I have these two properties, I can define a consistent truncation where I expand all of the fields of my theory in my basis of left invariant fields, or my global frame. And the coefficients will be fields of the lower dimensional theory, and these will define a consistent truncation. So this is very nice, except for the fact that group manifolds are kind of boring. So we'd like to do something more interesting, And before I get to supergravity, there's a very instructive example that shows that actually this can be generalized. So consider the following theory. It consists of gravity, so I have an Einstein-Hilbert action, I have a scalar field, and I have a Maxwell field, and there's a non-minimal coupling between the scalar field and the Maxwell field with this coefficient alpha, that's just some number, that I can choose. It turns out when I choose this number correctly, there is a consistent truncation of this theory on a two-sphere to some lower dimensional theory. And this is quite miraculous. S2 is definitely not a group manifold, so it doesn't seem to fit into the previous picture. There's no symmetry argument that tells you that the modes you've kept will define a consistent truncation. And moreover, the truncation ansatz is a complete mess and was really a miracle that it was found in 2000. So what is going on? Well, it turns out for this particular value of alpha, where you can define this truncation, this theory of Einstein-Maxwell-Dilaton is actually just GR in one higher dimension. This is just the usual Kaluza-Klein theory. And then it turns out, okay, I'm actually doing consistent truncation not just on S2, but on S1 times S2. But if you look carefully, the truncation actually involved a flux of the Maxwell field through the S2. So this is not even a product, it's actually a vibration. And in fact, this S1 times S2 turns out to be the Hopf vibration of S3. And then you can understand what's going on. I'm actually performing consistent truncation in this larger theory, GR in one higher dimension, on a group manifold S3. And so now I have a global frame, and this global frame defines an algebra, and the consistent truncation is very easy. I just expand in my global frame. So what's the lesson here? The lesson is that I shouldn't take my Einstein theory with Maxwell and Dilaton fields and view them as separately. Rather, I should unify all of these fields into some larger geometric framework, in this case just GR in one higher dimension. And then in this larger geometric framework, this is where I should look for a group manifold, and it turns out there's a group manifold and hence a consistent truncation. So how can I use this for supergravity? In supergravity, I don't have Maxwell fields typically, I have some larger fluxes, like 7-form fluxes. Well, it turns out there is a way to do this, and there's a way to unify all of these fields, the metric and the p-form fluxes in supergravity, into some larger notion of geometry, and this is known as exceptional field theory or generalized geometry. And the reason for the exceptional is because basically the groups that then act on this larger space turns out to be the exceptional groups. The details are not super important, but then you can actually recover all of these consistent truncations that were known, for example, since the 80s, the 11D supergravity truncation on S7 to 4-dimensional maximal supergravity, but also a bunch of other ones. And the picture is like before. Now, rather than working with the fields of 10 or 11-dimensional supergravity, where the truncations are very miraculous, it turns out that if I rewrite these theories and unify all of the fields into my larger geometry in exceptional field theory, then there is some generalization of a notion of a group manifold, which allows me to define a consistent truncation. In particular, what do I have? I have a global frame, now of this larger geometry, so some generalized frame, if you want. And this global frame closes into an algebra using the notion of Lie derivative that exists in the theory, which is known as a generalized Lie derivative. And then because of these two features, I can expand everything in my global frame, and I can easily show that I get a consistent truncation. Okay. So this is all nice. What does this have to do with AdS CFT correspondence? It turns out that certainly all of the maximally supersymmetric backgrounds, like AdS 4 times S7, AdS 5 times S5, but also many other ones define exactly such generalized group manifolds in this exceptional field theory. So in particular, I can describe the round spheres and these generalized group manifolds, and these have nice geometric properties, but also all of the deformations within the consistent truncation still have these very nice structures. And this is really powerful because these deformations might now break all kinds of symmetries and supersymmetries. They might be warped, they might look very complicated, but in this exceptional field theory language, they still have this very nice group structure which allows us to perform non-trivial computations. Okay, so how can we now compute the two-point functions of the CFT? Well, this is now very straightforward. We have two important features, as I said. We have these generalized group manifolds, which means in particular we have a global frame. The global frame means that we can expand all objects in our particular basis defined by the frame. And then I just need to worry about coefficients. So these are all going to be scalar objects. So I only need to use scalar harmonics. This should be contrasted with what I would normally do, where I would take all of the fields of supergravity and expand them in appropriate tensorial harmonics. So for example, the metric, I would have to expand in symmetric 2-tensor harmonics. 3 forms, I would expand in some 3-form harmonics. In this exceptional field theory language, everything is much simpler. I just need scalar harmonics because I have my global frame. Then I have this fact that I have some notion of left invariance because I have this notion of group manifold. And exactly like on a group manifold, this means that all of the differential properties become reduced to structures at a point. For a group manifold, I know that all the structures on the tangent bundle I can reduce to the Lie algebraic identity. Similarly here, because of this left invariant, I can reduce everything to a point. And so in particular, computing things like eigenfunctions and eigenvalues of differential equations reduces to an algebraic problem now of just computing eigenvectors and eigenvalues of algebraic matrices. So this becomes much, much simpler. And then the final point that's very nice for us is that all of these deformations are deformations of round spheres. And so what should we use as these scalar harmonics? Well, we can just use the harmonics of the round spheres. These are the same topological spaces. And it turns out this basis for the round sphere is actually extremely useful for us. And so all of this computation has become very straightforward. So now let me show you what you can do with this. My first example will be, again, related to AdS 5 times S5. So I have, of course, the maximally supersymmetric AdS 5 times S5 vacuum, dual to n equals to 4 super Yang-Mills. I have a consistent truncation on S5 with some interesting potential. This potential, with 42 scalar fields, turns out to have one supersymmetric vacuum. And this supersymmetric vacuum preserves just a quarter of the supersymmetries. And it breaks SO6 to some SU2 flavor and U1 R symmetry. And in this CFT, this corresponds to some mass deformation of n equals to 4 super Yang-Mills. But now we have all of these nice tools, so we can in particular compute all of the 2-point functions for all the single trace primary operators and compute their anomalous dimensions. And this is really quite striking. We can find in particular some closed form for the anomalous dimensions in this strongly coupled CFT for all of the single trace operators. And this is related to simply the charges of the symmetry groups that we have, things like the Lorentz group, the charge under the U1, the SU2 flavor charge. But also quite interestingly, we also get a relationship to the Kaluza-Klein level of the original 5-sphere. So this is already something puzzling from the CFT. Why do we have this relationship to the 5-sphere level? But in the supergravity, in the way we're doing it, this is completely normal. This is completely natural. Moreover, you see there's a square root in this formula. So for generic values of these charges, these conformal dimensions will be irrational, corresponding to unprotected operators. But for special values of these charges, the square root will disappear, and this will actually become the conformal dimensions of semi-short multiplets. And these you can then check with the usual AdS CFT tools. You can compute the superconformal index for the CFT, and these exactly match on the nose. But then there's, from my perspective, the more interesting questions: what about the long operators? Can we develop new CFT tools to actually check the prediction here for the long operators, and to be able to actually see their conformal dimensions from the CFT computation? Or maybe even less ambitiously, why are there finite conformal dimensions for unprotected operators at strong coupling? This is a very strange thing from the CSP perspective, from the supergravity. This is something we immediately find for these less supersymmetric cases. So this is a puzzle that I want to leave with the audience. How come we have these finite conformal dimensions at strong coupling for unprotected operators? Okay. Let me show you some other things we can do. It turns out these Kaluza-Klein masses are really nice observables to actually study the geometry because they're gauge invariant. And this actually allows us to learn about the geometry in a much simpler way. To demonstrate this, consider the following example. There's some interesting 4D supergravity whose details are not important, but it has two moduli, two directions in the 4D potential which are flat. I call these var phi and delta. For any value of var phi and delta, I have some n equals to 2 AdS4 vacuum. And in general, I have just very small isometries, U1 times U1. But for special values, I get symmetry enhancement or even supersymmetry enhancement. One of the puzzling features from the AdS CFT perspective is that in supergravity, these moduli appear to be non-compact. The AdS4 vacuum seems to be different for any value of these two parameters. Whereas from the CFT perspective, there's some general arguments that this space of conformal manifolds should be compact. So what could be going on? Well, you might say this 4D supergravity has nothing to do with string theory of quantum gravity. Maybe it can't be UV completed. But we can show that this does actually come from a consistent truncation. So this is some slice of type 2B supergravity or type 2B string theory on AdS4 times S5 times S1. And in particular, you can uplift, in principle, the full two-parameter family of AdS4 vacua to type 2B string theory. However, in practice, this is extremely difficult to do. So instead, what we did is to just study the Kaluza-Klein spectrum as a function of these moduli to try and better understand what's happening in the geometry. And we, for simplicity, just focused on one of the moduli, this var phi direction. So we looked at what happens to the Kaluza-Klein spectrum as I change var phi. And I'm showing you the result, the Kaluza-Klein spectrum as a function of var phi. And here I'm going to show you the lowest lying levels on the S1. And you see, indeed, var phi, as var phi increases, some things are independent of var phi and some masses increase, but there seems to be no periodicity. But now we can use the tools and compute higher Kaluza-Klein levels. And you see something interesting, that higher Kaluza-Klein masses actually become light as var phi increases before they become heavier again. And if I keep going to 10, this picture starts looking very nice. And if you stare at this for a few seconds, you notice it's very symmetric around this halfway point. In fact, you can show the Kaluza-Klein spectrum is exactly the same at this point, var phi is 0, as when var phi is shifted by 2 pi over r, where r is the radius of this circle in the background. So this suggests that actually maybe var phi should be compact because the Kaluza-Klein spectrum is periodic. And with this new insight, we could then go away and actually study the geometry, and we could show that indeed var phi is actually a compact modulus, but this is not seen in 4D. This is only when you include the higher Kaluza-Klein modes, and it's related to some complex structure deformation of the background. More interestingly, this is not something isolated to this AdS4 times S5 times S1 background. This happens whenever you have some AdS background times a compactification times S1. So as long as you have some S1 factor, you always have moduli of this type where you mix local U1s on the compactification with the S1. And in particular, depending on which U1s you choose, you can choose these moduli to be either supersymmetry preserving, like in this example, or even supersymmetry breaking. What's nice about the supersymmetry breaking moduli is that these have very nice properties. In particular, the AdS vacua are fully perturbatively stable, and they even seem to have nice mechanisms that protect them against other instabilities, in particular non-perturbative instabilities, alpha prime corrections, and so on. So one of the interesting questions I think coming out of this is, what is the fate of these non-supersymmetric moduli, which in the CFT should correspond to some exactly marginal deformations? Could we be having some exactly marginal deformations in CFT which are non-supersymmetric? Okay, and then finally in the last minute or so, I want to extend this. This was all about 2-point functions. I told you I was going to talk about 3-point functions as well. It turns out we can actually do the discussion for general endpoint functions. These are related to the endpoint couplings in supergravity, and we can show, because everything is controlled by scalar harmonics, that the supergravity couplings vanish whenever the scalar harmonics don't contain a singlet in their representation. So this integral has to be non-zero for the couplings to be non-zero. And what's very nice about this is it means that many, many more couplings vanish than you would expect based on the symmetries of your backgrounds. So just as an example, if I do this for AdS 5 times S5, even for the maximally supersymmetric background, you find that couplings vanish, which don't obviously need to vanish because of SO6. So for example, the chiral primaries transform in the symmetric tensor representation of the vector of SO6. So SO6 group theory would tell you if I have n of these, there has to be a singlet for the coupling to exist. So this gives you some condition, some kind of polygon condition on the Dynkin labels. But actually, this XFT analysis shows that many more couplings vanished. So for n points, whenever this condition is less than or equal to 2 times n minus 3 rather than just 0, we can show that these couplings vanish. And in particular, this proves some old conjectures about supergravity couplings by various people, including Boris, who is here, about near extremal couplings in supergravity. Even more interestingly, this means that infinitely many endpoint functions in the CFT vanish, even though the symmetry doesn't require them to vanish. So what is going on here? There seems to be some relation with having this consistent truncation, which allowed me to use scalar harmonics. And this leaves me on my final puzzle, which is what is the meaning of all these consistent truncations from the perspective of CFT? For us, it was very important that we had these consistent truncations to some maximal supergravity. That allowed us to perform many computations of supergravity. What is the meaning of all of this in CFT? How could I know that a CFT is part of some maximally supersymmetric truncation or not? In particular, the most naive thing you might think is that these are all going to be deformations of n equals to 4 super-Young Mills or ABJM. But that's not true. The consistent truncation doesn't need to have any vacuum that preserves all of the supersymmetries. It could be that all the vacua preserve some supersymmetry. So this is a very strange statement, even in supergravity. And I'd love to know, what does this mean from the CFT perspective? What makes these CFTs special? And let me end with that. Thank you.
Questions? Oh, sorry.
Just a very short one. I mean, we had an argument about n equals 2 near extreme correlators to vanish because of some charges when we had differentiated in the coupling. That was charge counting. But it's one of your list, I guess.
Yeah, the example I showed was AdS 5 times S5, and there is, as I mentioned, this n equals to 2. I mean, I should actually check. N equals to 2 for you is in the CFT or the AdS? Like
n equals to CFT, or? I mean, n equals to CFT.
Then, yes, so then, okay, I wouldn't be able to do this AdS 5 example, but there's other examples. There's certainly lots of these near extremal couplings that would vanish, but this notion of near extremality is really something I think that becomes less useful for less supersymmetric backgrounds. So certainly there would be many, many couplings that vanish, some of which you would call near extremal, but also others, that's for sure. Yeah. But I don't have an argument for why from the CFT, if that's your question, only from the supergravity.
Yeah, no, I was just wondering whether you can pin out some kind of consistent truncation which would give you exactly that, but maybe we can...
Yeah, I mean, so the thing here is we're really finding that we're showing that infinitely many couplings vanish. So this is really beyond the consistent truncation. The consistent truncation would be like that couplings between finitely many fields and some other ones vanish, but here this is some generalization where even for higher Kaluza-Klein levels, you get relationships between couplings that vanish.
More questions? Yeah, coming.
You had several examples of non-critical dimension. For instance, this Einstein-Dilaton-Maxwell case. I mean, are you sure that these cases obey the vanishing of the one-loop beta function?
Yeah, the Einstein-Maxwell-Dilaton was really just a toy example. This doesn't even have an AdS vacuum, I don't think. So that's really just some toy example, but all of the other examples are real supergravity ones that are some low energy limit of string theories.
Well, it's obvious for the critical dimensions, but it was less obvious for the cases that it took non-critical dimensions.
Yeah, so apart from this Einstein-Maxwell dilaton, they were all always parts of a consistent truncation of 10 or 11D supergravity, so they were always critical.
Any other question? Then let's thank Emanuel again. Thank you.